Hello, so my name is Millicent Malinga, and I'm going to be sharing with you the overview of the SIR model and give you a walkthrough of the technology that we can use to solve this model. So first of all, what is the SIR model? The SIR model is calculus model that is used to model the spread of epidemics. So this means that we can use it to predict how an epidemic is going to behave in a given population with certain values provided or calculated. So S in our susceptibles, S stands for susceptibles in our population, the people who are at risk of getting infected, I stands for infected, and R stands for removed. So removed is actually people who've either healed, recovered from that infection, and will not ever be susceptible again or infected, and or have died. Yeah, that's the dark part about it. So this is a set of differential equations, ODEs. The first one is to give us the susceptibles at any given point in time, which is calculated by beta, which is the rate of interaction between the infected and the susceptibles, and then multiplied by I and S over N, right? N is our total population. And then the same applies here. This is, so anyone sane enough would understand that negative, like this BIS value, beta IS value, is the number of susceptibles that are getting infected. So we are subtracting from susceptibles going to infected. So we'd expect this to be added to the infected number, and we'd expect to remove those who are recovering, and they make up the removed, right? So let's go down and take a look at this. Now we have our differential equations here, right, showing under N, right? And then at start, these are values. In the beginning, actually, R at T0 is equal to 0, right? And we also have one really important equation, which is S over N times beta, right? Divided by mu. So all this, right? This is S naught, by the way. So at the beginning of our pandemic, we can be able to tell whether or not, at the beginning of this disease model, we can be able to tell whether or not we're going to have a pandemic, an epidemic, if this is greater than 1, right? So we're going to see this in the graph that I'm about to show you. And then when we come down here, we have, this is Euler's method, which I will not get into, but you can come through the document and walk through it and understand what it's about. This is how we solve this set of these 3 equations, where this is the function of the differential of this equation involving x, y, and z, and then this one is for the other equation of y, and then this is for z, all at time t. And then our step now is how we are iterating through these days. Like, for example, here when we say xi, right? So how are we stepping to get to xi, right? Maybe we are moving at 2 days, or we're moving at 1. You know, our step is 3, right? You're going to see this come into play in the graph, right? And then that's it. That's what we have. And this is our solution, our set of equations that we will use to model this graph. So the purpose of this model is to help us to put into place measures that will help us reduce at any given point in time, both I and R naught, which is the rate, the reproductive number, the rate at which people are getting infected every day, right? So now let's take a look at our model in Excel. So I used Excel to create this model, and then I had my own values of beta and mu. So my beta is 0.2, and then my mu is 0.1. So this is actually the rate at which people are recovering or dying, right? Right. So we were talking about new. This is, like we said, the rate at which people are recovering or dying, and then this is the rate at which the infected and the susceptibles are interacting with each other. Right. So when we come here, what we have now is this, right? Formula that I've put in here is simply n at the beginning minus I here, right? This is what we have, F3 minus C2. That's the beginning of our S, that's S naught. R naught at the beginning is 0 because we've not had any recoveries or deaths. We're trying to see how we can reduce these, right? We can try and see how we can reduce the infections and the deaths, hopefully. So what happens with this model is that we've tried to model it for about a year, see how we'll progress throughout the period from November 2021 to November 2022 if we continue to have this Omicron in our midst. So at this point, this is our graph, right? This is the graph that we have. As you can tell, after 120 days, we'll be at our peak, which will be still, if we go to 120 days in our graph and just check in our table, just to see how much people will be infected at that time. So this is 120, and we'll have about 313 infections, right? 313,000 infections. They will not, it's 121 actually, this will be our highest, 314,291 infections. They will not go beyond this number, right? So our highest number of infections will be 300 and roughly 15,000 of people will be infected by then. And during this time. So this will probably be the time when, we claim to be having the fourth wave after 3 months of having discovered this virus, if it is following these constants where we are having our rate of recovery at 0.1 and the rate at which people are infecting each other 0.2, right? So now when we come here again, this is our graph, this is how it looks. This is the way the susceptibles will reduce because they are growing in the removed part of it. So now, whether or not these people live or die is not up to this mathematical model to decide. What we know is that they will be reducing in the susceptibles. So they could either be dying or recovering according to the strength of their immune systems. But what remains constant is our N. So what can be done to help reduce all this? So if we come up here, what scientists have been doing, what they tried to do was to say, put on your masks, stay at home. What they were trying to do at this point was to reduce beta, right? And so even though susceptibles was remaining constant at this point, maybe if we have this at like that, or let's put it at 0.1 and see what happens to our graph. So if we look at this, look at our numbers. Let's go to day 121 and see that was at our peak. Now let's come back here and check it out. Day 121, we have 18 people infected. We have 226 recovered. So that means that we are really, really staying safe, right? This is what we're doing. And if you can look at that, we cannot see the I or the R because they are way lower and our scale is starting from 500,000. But what's happening is that our people are staying safe, our people are okay, right? And our S is also staying constant below this orange line. How else can this model help? This model can also help scientists calculate how many people we need to vaccinate as fast as possible so we can reduce the number of susceptibles, right? So that's what this model is doing to help people fight the pandemic. So this is the model that was used to help us come up with decisions on how long people should go into quarantine, how long people should go into lockdown, why people should wear masks, sanitize, and all these things, how many people should be vaccinated by which period of time so as to ensure that the epidemic spread is not as the model states, right? So this is just about it when it comes to the SIR model. So the next time you're told, put on your mask, just know that the scientists know what they're saying, the epidemiologists know what they're talking about. Yep. You save that. Okay, this is taking way more than I expected. Let's just go back to this part. Right, so in this part, I would just like to say